In this video, I will show you how you can solve a constrained minimization problem with mixed constraints. That is, it has equality constraints and inequality constraints. Let's start with the following minimization problem. You want to minimize respect to Q1 and Q2, C1, Q1 plus C2, Q2. And we have three constraints such that Q1 is greater or equal to 0, Q2 is greater or equal to 0, and Q1 plus Q2 is equal to Q bar, which is strictly greater than 0. So we have three constraints here, two inequality constraints and one equality constraint. Note that this equality constraint has a Q bar in it which is strictly greater than 0. Now this looks like a standard cost minimization problem. Let us further assume that these two functions here, C1 and C2, are strictly increasing and strictly convex. If they satisfy that condition, we can solve this. Okay. Before solving this, we need to check the constraint qualification and put all the constraints in the right form. So let's start with that. All inequality constraints need to be less than or equal to 0, and all equality constraints need to be equal to 0. So we get minus Q1 is less than or equal to 0, minus Q2 is less than or equal to 0, and we have Q1 plus Q2 minus Q bar is equal to 0. Okay, now they're in the correct form. Now we can check the constraint qualification. Let's set up the gradient matrix of all these constraints. Let's call them G functions, these constraints, and then we get our gradient, which is equal to minus 1, 0, 0, minus 1, and 1, 1. Just taking derivative of all three respect to Q1 for this column and respect to Q2 for the second column. Okay, now we need to check in all cases if this has full rank. So we need to have the matrix of gradients of the binding constraints have at least the rank of either the number of binding constraints or the number of variables you maximize or minimize with two. Here we have two variables. We have potentially three constraints. So if only one of them is binding, we need to have a rank 1. If two or more are binding, we need to have a rank 2 because there are two variables. Let's go through all cases. Now, because the third one is always binding, we always have this third one. So we're left with 3 or 4 cases. We can have these two binding, we can have these two binding, or we have all three binding. Now we can immediately exclude that all three are binding. The reason we do that is we look at these three constraints here. If this one is binding, Q1 is 0. If this one is binding, Q2 is 0. Q1 plus Q2 will be equal to 0 if they're both 0, which will violate this strict inequality. So we can never have the case where all three are binding. So we're left with three cases, either this binding, the bottom two, or the top one and the bottom one. Okay, let's start with only this one binding. If only this one is binding, we only have this vector here, which we need to look at. And this vector is not the 0 vector, so it has full rank. That's satisfied. Let's call this 1, this 2, and this 3 for convenience. And so we have two more cases to check. 1 and 3, and 2 and 3. So 1 and 3 are binding, or 2 and 3 are binding. If 1 and 3 are binding, we don't worry about this middle row. and this remaining matrix needs to have rank 2. Now, the top row is linearly independent of the bottom row, so we have this condition always satisfied. And if we have 2 and 3 are binding, we don't have this top row, and we have this matrix down here. And again, the top row is linearly independent of the bottom row, so it has full rank. Altogether, the constraint qualification holds at all points. Okay, so now we can set up the Lagrangian and solve this problem. Let me erase this. And now we set up the Lagrangian. So usually the Lagrangian is set up that we have the objective function minus lambda 1 times the first constraint, lambda 2 times the second constraint, minus lambda 3 times the third constraint. Now, we have two differences here. First one is we have a minimization problem. If we want to minimize this function, we need to change it into a function we can maximize. Well, the minimum of this function is the same as the maximum of this function multiplied by minus 1. For example, if I minimize this function, I get this point. If I maximize the inverse, or minus 1 times multiplied this function, I will get as a maximum this point, which is the same point. Okay. So we dealt with the minimization problem. Now we need to deal with non-binding and binding constraints. The non-binding constraints, we can use the standard approach, minus lambda 1 times this constraint, minus lambda 2 times this constraint. The equality constraint here we need to treat as you would treat it if you don't have any inequality constraints. So let's call the multiplier mu, and we say mu times this constraint. And we can set up our Lagrangian. L is equal to minus C1 Q1 plus C2 Q2 minus lambda 1 minus Q1, so plus lambda 1 Q1 plus lambda 2 Q2, and third constraint minus mu times Q1 plus Q2 minus Q bar. Okay, let's now take first order conditions. Again, we want the minimum of this function, so if we multiply it by minus 1 as we did here, we want to find its maximum. Let's start with the derivative with respect to Q1, which will be equal to minus C1 prime Q1 plus lambda 1 minus mu equals 0, and the derivative of the Lagrangian in respect to Q2 will be minus C2 prime Q2 plus lambda 2 minus mu equals 0. This function is completely symmetric, so once we have this, we get this immediately. Then we have the set of conditions for the constraints here. Let's start with the first constraint we have. We have that Q1 must be greater or equal to 0, lambda 1 greater or equal to 0, and we need to have that lambda 1 times Q1 is equal to 0. The same expression needs to hold for 2, right? Because it's lambda 2 times Q2. So we can simplify and change the 1's into i's here, and say for I equals 1 and 2. That leaves us with this equality constraint here, so we simply need to have that Q1 plus Q2 is equal to Q bar. And these conditions here will give us the solution to this minimization problem up here. Okay, so as we discussed here with the constraint qualification, we have again three cases. The first case is where Q1 and Q2 are strictly positive, so we only have this third constraint binding. Then we can have that Q1 is strictly greater than 0 and Q2 is equal to 0, while still this constraint being strictly binding. And the third case where Q1 is equal to 0, Q2 is strictly greater than 0, and still this constraint binding. Let's go through these cases separately. Case 1. Let's say case 1 is the case where both Q1 and Q2 are strictly greater than 0. Qi greater than 0, okay, for all I. If that is the case, we can look at this condition here. Lambda I times Qi must be equal to 0. So we have lambda I equals 0 for all I. Otherwise we violate this condition here. Now if lambda 1 and 2 are 0, we can have this expression which will become very simple. We get Ci prime Qi is simply equal to minus mu, all I. Okay? This lambda is 0, so we have minus C1 prime Q1 minus mu equals 0. So if you take this to the other side, we get minus mu is equal to C1 prime Q1, which we have here. And the last condition we have is here at the bottom, we have Q1 plus Q2 is equal to Q bar. Okay, case 2. In case 2, we have Q1 is strictly greater than 0. Q2 is equal to 0. This implies that lambda 1 equals 0 to satisfy this complementary slackness condition again. If lambda 1 is equal to 0, we can go back up here and we find the relationship between Q1 and mu. So we get C1 prime Q1 is equal to minus mu. Now we have the condition down here. Since Q2 is equal to 0, Q1 is equal to Q bar. And from here, we can get, this is not equal to 0. We know what this is from this condition here. C1 prime of Q bar is the same as minus mu. So we know what this expression is. We know Q2 is 0. So we know what this expression is. And we can get our lambda 2. And we will have that lambda 2 is greater or equal to 0 because of this. Case 3. Now we have Q1 equal to 0, Q2 strictly greater than 0, so we have lambda 2 equals 0, again from this complementary slackness condition. Then we have C2 prime Q2 is equal to minus mu. Then we have again this constraint. We have again this constraint here. So we have Q2 equals Q bar. And lastly, we have lambda 1 greater or equal to 0, which we can obtain by going into this equation. We know Q1 is 0, so we know the value of this term. We know mu is equal to, from this one, is equal to C2 prime Q bar, because Q2 is equal to Q bar. And so we can determine what lambda 1 will be. Okay, so we found our 3 cases. Which of the 3 cases will be depends on our functional forms. If we have exact functional forms, we can figure this out. Okay, Now we need to check second order conditions. With second order conditions, we can ensure that these three cases actually give us a maximum to this Lagrangian, which implies it gives us a minimum to this minimization problem. As I said in the very beginning, we assume that C1 and C2 are strictly convex functions. Similarly, all these constraints are linear. Because all these constraints are linear, they're all concave. Because they're strictly convex, minus this will be strictly concave. So we will have an overall concave Lagrangian. Since the Lagrangian will be overall concave, we know that these points will give us maxima. Thank you for watching.